Hello everyone, this is Shannon Rasmussen. I'm the Marketing Coordinator at eMaint Enterprises, and I just want to thank you guys for joining us for this month's Best Practices webinar. We're really pleased to have Jeff Shiver, CMRP and CPMM with us. He'll be presenting today's topic on the consequences of hidden failures. And just to tell you a little bit about Jeff, he's the Managing Principal for People and Processes, Inc., and has educated and assisted hundreds of people and numerous organizations in implementing the best practices for maintenance and operations. Recognized as a trusted advisor, Jeff has also worked with clients in educational, manufacturing, and facilities environments to improve their practices. Certified in the maintenance best practices and as an RCM2 practitioner, Jeff is a frequent presenter at multiple maintenance conferences and is published in various trade media outlets via articles and blogs. As such, Jeff leads many of People and Processes core training classes such as maintenance planning and scheduling, maintenance reliability for managers, supervision, and reliability-centered maintenance. Hello, Jeff. Thanks for joining us today. While people are logging in, I thought you could maybe just tell us a little bit about yourself and what prompted today's topic.
Okay. Well, Shannon, thank you very much, first off, for having me. It's always a pleasure to come with you and Rona and do these webinars for the eMaint crowd. And as part of that, you know, you ask about why this particular topic, and it's actually one that is near and dear to my heart, actually, from a reliability-centered maintenance perspective. And what happens is that these are, you know, so many of these hidden failures we're really not looking for. And as part of that, you know, they're hidden. And so to the extent, you know, these kind of things are what will cause environmental and safety issues within plants, and it's really been able to sleep at night at the end of the day. You know, from that perspective, with clear conscience, knowing that you've done everything you can to protect the people that, or, you know, the industry or the business itself. For example, if you take Deepwater Horizons, you know, in the billions upon billions, the last time I looked, I know it was in the $40 billion that were spent, you know, on that as an example, you know, with regard to the failure. There are a lot of different failures, but obviously the failure of the blowout preventer itself. So when we talk about it, you know, the consequences become huge, you know, with respect to that. And it's not just, you know, 40 billion, we can replace 40 billion. If Shannon was caught up in that, obviously we couldn't replace Shannon, you know, so that becomes a bigger concern. So that's really the basis for choosing this particular topic this month.
Over to Jeff.
All right, well, let's get started. And we talk about the consequences of hidden failures, and thanks, by the way, again, Shannon, but the consequences of hidden failures, if we think about hidden failures, the majority of hidden failures come from protective devices. And so we'll just start out there. And let me get down here and tap the screen. There we go. If we think about protective devices themselves, they're designed to do three things. They're either designed to protect people, like we talked about with you a minute ago, with regard to the Deepwater Horizons piece, and life and property, as well as protect machines or protect products. And in some cases, it can be a combination of all three of those. That said, recognize that there are 5 different types of protective devices. And when we look at the first type, the first type is intended to warn or alert operators about abnormal conditions. And so if you think about it, you have lots and lots of different protective devices. And in this particular case, we could use as examples level switches, load cells, overload or overspeed switches, vibration switches, proximity switches, temperature, pressure switches as an example. So again, these are only intended to warn or let the operator know that something's amiss. And then a second type is to actually physically shut down the equipment in the event of a failure. It can be in the form of a relay or an emergency stop, or very much like a pressure switch or other sensors. But again, a different focus is actually disabling the function that it's protecting as opposed to warning. The third type is actually intended to eliminate or relieve abnormal conditions which follow on after the functional failure and which otherwise might cause secondary or more serious damage. And when we look at those, we think about things like firefighting equipment as an example, or safety or pressure relief switches, or as you see there, ruptured disc or bursting disc, and even emergency medical equipment falls into that category. And the fourth type is actually to take over from a function that's failed in the case of like a standby plant, standby pump, standby generator. And it could also include things like redundant structural components, bracing of beams, for example. And the fifth type is intended to prevent dangerous situations from coming into play in the first place. As you can see in the case on the left-hand side of the guardrail on the road, it's not normal for cars to run off the road. So we have a guardrail there to protect it. In the event we have a primary failure that we have an incident where the car swerves off the road. If you look, for example, at the case of signage even, so I'll back up a step when we talk about dangerous situations arising in the first place, it'll be things like guardrails or even signage. And we look at signage, for example, you think about it, it's not normal to have a fire in a building, but in case of fire, we go and we use the elevators. And here we have a warning sign to make sure people we don't use the elevators in case of fire. So here the intent is to actually warn people. So you think about it from a preventive maintenance standpoint or an on-condition inspection, one of the things that you would actually do here is you would actually go look for signage or check the guardrail. So that said, how many protective devices do you actually have, within the organization? And you think about it, you have lots and lots. E-stops, interlocks, shear pins, check valves, rupture discs, like we talked about, gas detectors, as an example. And I'll go ahead and let you ask the poll question there, Shannon.
Okay, great.
We can barely hear you, by the way.
Okay.
That's better.
You guys can hear me now? Okay.
Yep.
So the first poll question is, considering the large number of protective devices, how many would you estimate are actually maintained? And hopefully you guys can all see this. The first is 30 to 50%, 51 to 70%, 71 to 85%, 86 to 95%, or 96 to 100%. So let me just give everyone a little bit more time to enter their polls. We see some coming in. See, we're at about 85% voted. See if we can get a little bit more. All right. Here are the answers. Here's what everyone said. It looks like most people said either 30 to 50% or 71 to 85%. And then a couple of you said 51 to 70, and then very few said 86 to 95% or 96 to 100%.
Yeah, and the question was how many are maintained? Because I can't see the question in front of me right here.
Yep. The question was how many are actually maintained?
Yep, and actually it's only about 30 to 40%. And if you think about it, unfortunately, a third of them, roughly, we're not even aware of. And there's no preventive maintenance being done, preventive or on-condition task, if you will, with regard to those protective devices. So yeah, it's actually 30 to 40%, are all that's maintained out of that batch. So good. Good. And when we talk about protective functions, recognize that there's a protected function, which in this particular case was the tire, and then we have a protective device, which was the spare tire. And this is kind of a little thing. I don't know where someone got this picture. I found it. But anyway, what they've done is shoved a tree limb up underneath the trailer, and they're riding down the road on the tree limb. And obviously, I hope they get as far as they wanted to go before it wears out. And they put the trailer back down on the axle. But it was, in this particular case, they used the tree limb as a spare. And a little different approach. But when we think about it, when we apply it to like machine guards, here you have a protective function that's the mesh door itself, and that's intended to keep people away from the equipment. And then you have a protective device itself, which is the interlock switch. And let me flip here. So, and when we talk about fundamentals with regard to protective devices, they're often in more need of routine maintenance than the devices they're actually protecting. And conversely, because we have protected devices, we don't have to do as much on the protected function from a maintenance perspective. And we can't develop a sensible maintenance program for protective function without also considering the maintenance requirements for the protected device itself. And I'll give you a case study to demonstrate some of this, and this really comes back to the consequences of hidden failure. In this case, it was pretty severe. He had a 29-year-old male operator that died when he was caught in a plastic injection machine between the injector and the housing. And what happened when they went back and did the study to figure out or determine the root causes, what they found out is that the individual had never received any training specific to the machine itself. But more so, the protected function, which was the hand shield, had a safety interlock device that had failed and was in the failed state. And then in addition to that, the maintenance management system did not document when the inspection had occurred. Matter of fact, there was no documentation that any inspection had ever occurred. And I'll share with you guys something about this too. Recognize from an OSHA standpoint or any other regulatory agency, when you have an incident in your factory, one of the first places they're going to look is inside your CMMS system. And they're going to look and see, have you been doing the maintenance that you need? So this is where, number one, we want to defer any of our maintenance strategy items or our maintenance task, if you will. And then in addition to that, we will make sure that we document that we did them, both in a timely fashion and completely. And I'll add on here, there's always an issue that as I go into many different plants, it's an issue where the technicians aren't giving good feedback. And as part of that, I always encourage the technicians to basically think of it as they're writing themselves a note, because it may very well be them that comes back to a particular machine or something 2 years from now and says, okay, what did you do? And at this point, they can go back and look and say, well, the last time we had to do something on this machine, this was what it was. And so that highlights the need from a regulatory standpoint of we want to capture good data in the CMMS and be able to actually show, yeah, we did inspect these devices. So let me go ahead and ask another poll question here, Shannon, if you will.
All right, let me launch this. Our next poll question, number 2, is based on studies, what percentage of hidden devices are already in the failed state? The options are 10%, 20%, 30%, 40%, or more than 40%. So let me give everybody a chance to answer. All right, looks like everybody got a chance. Okay, so again, the question was, based on studies, what percentage of hidden devices are already in the failed state? Looks like most people said 30%, and then after that, more than 40%, and very few said 10% and 20%.
Actually, what studies have shown is 20%. So you guys were a little high, but that's erring to the safe side, so that's a good thing. Yeah, actually, 20% is what the studies have shown. So continuing on with this here, the protective function, as we said earlier, was the hand shield, and of course the protective device was the safety interlock. And here's another case study for you, and you guys may recognize this one, Piper Alpha. It's a case study from 1988, and in this particular case, what happened is you had 2 pumps with pressure safety valves, and one pump's pressure safety valve was removed for maintenance, and what they done is they put a note in the control room and said, you know, under no conditions should you start pump A because the pressure safety valve has been removed. And during the night, the pump B actually stopped, and they restarted with pump A, and of course led to an explosion, which 167 people were killed and 3.4 billion lost. And it was all simply because the protective device was not there. And so the outcome from the Piper Alpha case was the inadequate maintenance and safety procedures were recognized, and it led to 106 recommendations for changes in the procedures in the North Sea. So when we talk about failure consequences, and the way we identify hidden devices is, would the functional failure of the device be evident to the operating crew under normal conditions? And if it is, then we call it evident. When we talk about fail-safe protective devices, it means that the failure of this device on its own will become evident to the operating crew under normal circumstances, because that's the intent of a fail-safe device. And so the failure is evident, and so it falls into operational or non-operational consequences, as opposed into the case of a hidden consequence, if you will. And one of the things you have to watch out for, though, is that many items they'll label themselves as fail-safe, but it's not actually fail-safe. And I put this here as a demonstration of that. For example, you've got a float switch out there, and the float switch has normally closed contacts, and so as long as the ball's not raised, you should be getting a signal to the PLC or to whatever the safety circuit is. And as part of that, what happens is you have power on, but the power on doesn't mean that the ball doesn't have that the float doesn't have a hole in it, or that the contacts aren't welded shut, or the mechanism isn't corroded. See, so from a reliability-centered maintenance perspective, what happens is you put it into actual failure conditions where possible. So in other words, to actually test this, we would raise the level of the tank, for example, to reach the float and actually see if it opened, and that's how we would test that. So in this case, people would say, okay, well, that's fail-safe. Well, no, it's wired where the contacts are normally closed. It is not fail-safe. The only thing that shows you that you have power going through the circuit. That's all. So when we're talking about this, we said that a functional failure on its own will not become evident to the crew under normal circumstances. And when we talk about normal circumstances, there's some caveats to that. And one says that, normal circumstances. One is that the failure on its own, that nothing is being done to prevent the failure. Nothing's being done to prevent the failure, and no specific task is being done to detect it. And from a reliability-centered maintenance standpoint, what we do when we do analysis inside the RCM world is we back it down to where we're not looking at what the tasks are being done and exclude those. We look at it from a baseline of nothing's being done. And the intent with that is you actually want to determine if the tasks we're doing are valid. In many cases, you look and you find out that when you go through an RCM analysis process, as much as 40% of the PM tasks that are currently being done are worthless and not value added. And that's one of the neat things about reliability-centered maintenance is it goes through and it tells you, are we doing things that address the failure modes of the equipment rather than just doing manufacturer-directed tasks as an example. Because what happens, for example, with manufacturing-directed tasks is they truly don't know the failure nodes. I work with a number of OEM companies, and when you go back and you talk to them, they say, well, what did you base your warranty or your PM recommendations on? And they say, well, just the seat of our pants. And they said, we've got warranty information for the first 6 months or whatever the case may be, but beyond that, we don't get any information back. And they said, well, what about like your hydraulic pump manufacturers or whatever? And they said, well, we don't really get information from them either. And so you have to be careful using OEM guidelines, and again, that's the benefit of the RCM world. But when we talk about a functional failure on its own will not become evidence to the operating crew under normal circumstances, that's what we consider a hidden failure. And let me give you an example of what a hidden failure might look like. In this particular case, again, asking the question, will a functional failure on its own become an evidence to the operating crew under normal circumstances? We have a tank, and the tank has a level transmitter that is maintaining the level. It's ultrasonic, and it's maintaining the level in the tank between 9,000 and 5,000 gallons. Now, the question I would ask you is the level transmitter itself, would the failure of it be evident to the operating crew under normal conditions? And you would answer yes, because obviously the tank would run dry or it would overflow. Now, if we actually have protective devices on that, and say we have a high level or a low level, now when we look at the high or the low, would the failure of either one of those switches be evident to the operating crew under normal conditions, under normal circumstances? And the answer is no. Because as long as the level transmitter, and I'll show it this way, if we look at the protective function, which is the level transmitter, and we look at the protective devices down at the bottom, as long as the level transmitter is functioning, you could have failed either the high or the low level, okay, and this is what the star is indicating there. And during this period here, which is label number 2, you're operating with no protection at all, and unbeknownst to you, okay? And then what happens is you finally lose the level transmitter itself, and at that point you've got no protection. And so if it was a caustic acid or or something, or you could damage the equipment by running it dry, you would have done that because you had no backup. So this is actually what we call when your protected device is already in a failed state, and then your protective function fails, we call that a multiple failure. And what you're trying to do is you're trying to avoid at all costs a multiple failure. And there's another thing that I'll mention here too that always comes up, and it's the question of time. And what happens is that it doesn't matter when the failure occurs. It could be weeks, it could be months, it could be years, but the question still remains for it to be hidden. Will the functional failure on its own be evident to the operating crew under normal circumstances? It doesn't matter if you find out 2 days from now, 2 hours from now, or 2 years from now. If it becomes evident, then it's not hidden. If it's not evident, in the case of like a high or low, then it's a hidden failure. And with regard to a strategy, for hidden functions, the challenge is we have to prevent or at least reduce the probability of the multiple failure, meaning the protected device is already in the failed state when the protected function fails. And as part of that, we have a decision tree, and the first options we get to in the case of a hidden failure, or a hidden failure would be proactive maintenance. Could we do an on-condition task first? And if we can't do an on-condition task, then can we do a scheduled restoration or scheduled discard? And if we can't do that, can we do a combination of those tasks? And if we can't do that, then we have to do a failure finding task. And that means that we physically go and inspect, for example, that high or low switch to see if it's already in the failed state. And we would do that based on some period time, every 3 months, every 6 months, every whatever. And really that's based on the unavailability of the switch. But without getting into all that for the purposes of this webinar, because you can actually get into and calculate the failure finding intervals. We call that FIFI. And so to do that, that's fine, but again, beyond the scope of the time we have here. And if you can't do a failure finding task, then if it's environmental or safety, then you have to redesign it. That's compulsory. And if it's operational or non-operational consequences, then you have the choice to redesign or simply accept the risk. And Shannon, there's another poll question for us.
Third poll question is, what percentage of your PMs asked to check items like alarm lights, buzzers, or other indicators for potential failure? There's 10%, 20%, 30%, 40%, or more than 40%. All right, we almost have everyone voted. I'm going to close this. And all right, so it looks like the majority of people, 27% said they think 10%. Then the rest of you thought more than 40% or 20%, with very few thinking 30% or 40%.
Okay, and there's no standard for that. It just depends on the individual process and the operating context. And I was just using that to find out what the audience thought. And for those that are the 27% that was at 10% or less, as an example, that's almost scary. And it comes back to having the conscience to go and check those things and make those part of the maintenance strategy, if you will, because it's really important that we find things that are in the act of failing, especially with regard, or in this particular case for protected devices, items that have already failed. Let me use this analogy. How many of you, and again, we're not going to ask a question from a poll standpoint, but if you think about the last time that you took a trip with the family, and you know, Shannon is a perfect example. You were talking about you were going to take a trip maybe in coming weeks, and so
right.
as part of that, you know, how many of you would have checked your spare tire to make sure that it was properly inflated and that it wasn't, you know, that it was serviceable, as an example, or that you even had one? So how many of you might have done that? And if you think about it, that's really a failure finding task. And so what happens is if you lost one of your tires, which would be one of your primary 4 tires or 2 tires in the case of a motorcycle, then the question would be, okay, do you have a spare? And if your spare was already in the failed state, then that would be what we call a multiple failure. So it's just another way to bring that home to people. And something to think about, Shannon, you need to check your spare tire before you head off.
Yeah, I don't think I would have thought to do that.
But many cars now actually,
yeah,
well, many cars now actually have, tire pressure gauges, indicators that come into the instrument panel, but still not necessarily for the spare tire. And so it's important to do that. Let's talk about strategies a little bit more. And so with regard to strategies, let's look at this pump. This is a duty pump, and it's just a standalone pump all by itself. So we think about the maintenance strategies that we would have for it, and of course we always start first with on-condition tasks based on the failure modes. So we could say, okay, the bearing would seize here, and the bearing motor would give us the bearing failure, bearing seizing, for example, would give us a total failure. And so to detect that, we might use something like vibration, or depending on where we're trying to find it, we might find it with infrared as an example from a heat standpoint. But if we look differently too at the impeller could wear over time, and based on what we were running, we may choose to use a scheduled restoration approach if we knew that the mean time before failure was roughly every 2 years, let's say, or every 6 years, whatever. We would go in and replace it in advance of that. And so when we talk about that, here are some of the strategies. We would lubricate the bearings. Maybe we would do vibration or ultrasound, for example, on the bearings to determine the state, and trend that to see how it's changing over time. And that's considered an on-condition task. And then we would do scheduled restoration task with regard to the impeller. But now let's contrast that to a standby pump, which, remember, we said standby was a protective device. So, and also before I finish here, this has operational consequences because it impacts the operation of the business. So now let's look at this where we have a duty pump and we have a standby pump. Okay? And let me go ahead and ask this poll question here. And the question really relates to the maintenance and also how you operate these pumps. Do you alternate? Do you use one as a duty and then when it fails switch to the standby? Or what do you do? And go ahead, Shannon, with that question.
All right, so it's up now. Are your redundant assets only used when the duty fails, or do you alternate between, or use equally between the 2 assets as an example? So this one just has 3 options: standby use only, alternate, or depend on the asset. See, we're about halfway there. All right. So it looks like almost half of everyone said it depends on the asset. And then about 32% said they alternate, and then 20% said standby use only.
Yep. Okay. Thank you, Shannon. And what happens here is if we look at the maintenance strategies that we apply in this particular situation, what we do is for the duty pump itself, we do no scheduled maintenance. And that doesn't necessarily mean run to failure now. That means no scheduled maintenance. So in the case of, for example, like the impeller, we wouldn't do that. It doesn't say we wouldn't run over there once in a while and do add lubricant, grease the bearing or whatever. But the point is in this case, it actually has, well, let's back up. There's no scheduled maintenance there. And with regard to the standby pump, the maintenance strategy there is we could do proactive task or failure finding task, because we're assuming that it's in the it's sitting there idle. And so what happens is almost like that spare tire. So what we have to do is we have to go and check to make sure that it's not already in a failed condition. So what that means is we would just, rather than bumping it over, what we'd do is we'd shut off the duty pump and we bring the standby pump up, and maybe we'd go for an hour or whatever the case may be to get it to where it's up to temperature. We might run vibration on it even if we wanted to, and we might find that we don't need that even. But again, you think about the cost, and if you look at the duty pump in this case, when you have the redundancy, you have non-operational consequences because all you do is you fail over to the standby, and again, failure finding tasks with respect to the standby. And in this particular case, would the failure of this pump be evident to the operating crew under normal circumstances? And the answer would be no. And so, because again, you're having to go do failure finding tasks, the operator just wouldn't know that that was down itself. Now, let's talk about something else too while we're here. And when we talk about, the alternating piece, what happens is for components that experience an end of life or wear out zone, where they have a repetitive MTBF, or mean time before failure, what happens is when you alternate, you're running both of those pumps to the same point. So let's say you started off with 2 brand new pumps, and the impellers are brand new, and then say that you've determined that based on your process, you get exactly 2 years out of impellers, for example. Well, now you're sitting here and then realize too that 80% of all failures are random. Okay, so when we talk about 80% of all failures being somewhat random, meaning that, well, if I look at a mining operation, for example, one in Central Florida, what happens is they pick up coral heads that are fossilized coral heads, and they run those through pumps, and they don't know when they're going to get them. And when they get them, needless to say, it damages the pump. And so there you have no opportunity. But in this particular case, when we're talking about like the MTBF that's consistent, what you've done is you've run both pumps to the same point by alternating, and then you don't know when either one's going to fail. Okay, so that's why you have the duty pump where it's wearing, and you're keeping the standby pump in pristine condition. That said, by the same token, and which comes back to the other piece around depending on the asset itself, it depends whether sitting would do more damage in the case of corrosion, depending on what you're doing, or the fluid locking up, for example, and solidifying inside the pump. So again, you have to look at it by the asset. But good point, though. So you notice that the maintenance strategies are different with regard to duty and standby, and there's non-operational consequences and hidden consequences. So.